So today we're going to talk about reaction stoichiometry. So I don't want this word to be scary for you. Stoichiometry is probably a new term for a lot of you, but all it really means is that if you're given the amount of something in a chemical reaction, you want to be able to use that amount to convert to an amount of something else. And I'm going to write down the definitions. In fact, most of this page is all notes, and then we're going to get to 4 types of examples. So you'll see 4 examples in this video. It should explain everything you need to know to do the homework and to do well on the quiz and the exam for anything chapter 7 related. All right, reaction stoichiometry. So chemical equations and their calculations. This involves converting from an amount of one substance to an amount of another substance by using the balanced chemical reaction. You'd have to have a balanced chemical reaction first, of course. So when I say the word amount of one substance, I mean mass, in other words grams, or moles, or atoms, or molecules. This video will talk about going from moles to mass, mass to moles, mass to mass, and one other one that skips my mind right now, but we'll definitely get to it in the example. Now, it's important to remember that coefficients, the big whole numbers that we put in front of formulas, the coefficients in the balanced equation correspond to the relative number of moles. Okay, so the relative numbers of moles, and I've underlined that twice, that's important. A balanced reaction or a balanced chemical equation, those are mole ratios between the different reactants and products. Okay, not grams. So the first one we're going to do is the simplest. This is a mole-to-mole calculation. All right, so first I'm going to set up the problem. It says, consider the following balanced reaction. So luckily, this one's been balanced for us. It's Fe2S3 plus 6HCl yields 2 FeCl3 plus 3H2S. It's balanced and done. Here comes the actual question for us. How many moles of iron 3 chloride are produced? That means it's on the product side, right? How many moles of iron 3 chloride are produced when 0.023 moles of HCl are reacted with iron 3 sulfide? All right. Now, they just mentioned the iron 3 sulfide, but they didn't tell us anything about it. So I'm going to focus on what they did tell us about. They said 0.023 moles of HCl. 2 sig figs, by the way. So my answer will be 2 sig figs. Start with what you're given and put it over 1, just like we did in the early weeks when we did unit conversions. So I'm going to start with what I'm given, put it over 1. I put it over 1 to realize moles of HCl in the numerator. I use the balanced equation to get out of 6 moles of HCl for every 2 moles FeCl3. My answer, 0.0077 moles of FeCl3. So I got from moles of HCl to moles of FeCl3 in one step. That's the balanced equation. If you remember, the 2 in front of FeCl3 and the 6 in front of HCl, those are moles, mole ratios. Next example is when we go from moles to mass. So it says aluminum hydroxide reacts with hydrochloric acid to produce, that's the reaction arrow, to produce aluminum chloride and water. The question is, what mass of water is formed when 2.40 moles of aluminum hydroxide reacts with the acid? So I immediately hone right in on the 2.40 moles of aluminum hydroxide. But I can't do anything yet because I don't have a balanced equation. And oh shoot, they've given me the words, not the formulas. This is why naming is important. Chapter 6, we learned how to name this stuff. Aluminum hydroxide, AlOH3, plus HCl yields aluminum chloride, AlCl3 plus H2O. Why have I split up my H2O into HOH? Well, in video number 1, we recognize if there's an OH on the left, a hydroxide, it's helpful to split up my water into HOH. So I'm mentioning that again here. Rewrote H2O because H2O can be H parentheses OH when OH minus is on the other side. Made it much easier to balance. And I balance the OH minus as a chunk. So the H inside of OH minus is not an H. It's part of my OH. Start with what you're given, put over 1. 2.40 moles AlOH3. I've got to get out of moles of AlOH3 and into moles of water. So for every 1 mole of AlOH3, 3 moles of water, that gets me into moles of water. Now, for every 1 mole of water, there's 18.02 grams of water. Where did that come from? Where did 18.02 come from? Well, that comes from the periodic table, right? That's molar mass. So, mole ratio from the balanced equation gets me into moles of water. Using the molar mass, in this case, it looks like I'm multiplying by the molar mass. It's always per 1 mole. That's grams per mole. That gets me into grams of water. So that was a two-stepper. Okay, third example. Instead of going from moles to mass, we're going to go from mass to moles. All right, this is the one I forgot in the beginning of the video. So let me set up the problem first. So there'll be a bunch of background information here. It says, in photosynthesis, plants convert carbon dioxide and water into glucose according to the following balanced equation. So thankfully, they're going to give us the balanced equation here, right? We don't have to dream up what carbon dioxide and water is and what glucose is, although I would never make you need to know glucose, not till we get to the middle of the course. But anyway, it says 6 CO2 plus 6 H2O yields 6 O2 plus C6 H12O6. All right. Says a particular plant consumes 37.8 grams, 3 sig figs. My answer will be 3 sig figs. A particular plant consumes 37.8 grams of CO2 in a single week. Assuming that there's more than enough water present for all of the carbon dioxide to react, how many moles of glucose are formed? So start with what you're given, put it over 1. 37.8 grams of CO2. Grams is not a good place to be in. Let's get to moles. In this case, I'm dividing by the molar mass. And you just look at the units. You got grams of CO2 on top. On the periodic table, CO2 weighs 44.01 grams per 1 mole of CO2. I got to get out of moles of CO2. So in the balanced equation, for every 6 moles of CO2, 1 mole of C6H12O6. 3 sig figs is what I started with. My answer has 3 sig figs. So it's 37.8 divided by 44 divided by 6. 0.143 moles. Okay? You should double check that one. Do the math on that to make sure. Because you have to divide by 44, divide by 6 to get 0.143 moles. Okay? All right, the last one is the longest one because we're going from mass to mass. We'll need the periodic table twice. Okay? So we got a following reaction. I see a big old coefficient 4 that immediately makes me know it's balanced. It says if 1.6 times 10 to the third grams of NO2 reacts in excess O2 in water, how many kilograms, careful on the kilograms, of nitric acid, HNO3, are formed? Okay, start with what you're given, put it over 1. If you don't like 1.6 times 10 to the 3, you can just call it 1600, right? 1.6 times 10 to the third grams of NO2, divide by the molar mass. So it's 46.01. Where does that come from? Well, I'll tell you at the end of this, but it comes from the periodic table. Nitrogen and 2 oxygens weighs 46.01 grams. So I started with grams of NO2. After the first step, I'm in moles of NO2. For every 4 moles of NO2, I can bunny hop to HNO3 because every 4 moles of NO2, 4 moles of HNO3. That gets me to the one I want. And then I multiply by the molar mass of HNO3. And if I were to stop after the 63.02 grams, my answer would be in grams. I have one last step, and that's for every 1,000 grams of HNO3, there are 1 kilogram of HNO3. My answer, 2.2 kilograms HNO3. You might have gotten a lot of digits on your calculator, but I started with 2 sig figs. The answer is 2.2 kilograms. Where did all these guys come from? Well, the molar mass of nitrogen dioxide, NO2, is 46.01. I used the periodic table again to get HNO3, 63.02. And then the mole ratio. The mole ratio is how I can bunny hop from one guy to the other within the equation. Okay, so that's very important.